Okay, with that discussion of the time-independent Schrodinger equation in hand, for systems that we might be interested in, right, that have wave functions that are eigenfunctions of the time-invariant Hamiltonian operator, and those are lots of systems we might care about, it turns out, one would normally sort of illustrate how this is useful by going through a set of simple examples of increasing complexity, showing how one could apply that time-invariant Schrodinger equation to solve for wave functions and properties of important quantum mechanical systems. This can get a little involved, and I'm not going to go in any deep detail. I'm just going to focus on the simplest possible example of how this works and how this is linked to this idea of quantized energy, specifically because that is going to relate to something we care a lot about right now, which is absorption of light by molecular systems, right? Okay, and the example we're going to use here is, of course, the sort of solution for the wave function and energy of a particle in a one-dimensional box. Right? I know that sounds silly, right? But the reason for it is it makes the math a whole lot easier, right? So imagine we have a box, right? It's going to look something like this, right? Okay, and so on this axis, which we're going to call the x-axis, our box has a dimension running from, let's say, 0 to a, right? And our particle exists in this one-dimensional space, right? And on our y-axis here, we have energy, right? Okay. Now, remember, we need to think about what a Hamiltonian operator would look like, because we want to solve for the wave function of this particle in this one-dimensional box. And recall again that our Hamiltonian is going to be a sum, our quantum mechanical Hamiltonian operator is going to be a sum of both a kinetic energy operator, right, and a potential energy operator, right? Okay, but to make this easy, we're gonna constrain things in a big way. You've already seen me do this a little bit. I'm gonna do a lot more of it through more examples of other things, right? Inside the box, we're just gonna make this sort of simple. We're gonna say that inside the box, right, our potential energy operator is equal to 0, right? And outside the box, we're going to say our potential energy operator is equal to infinity, right? So there's an infinite inside the box potential energy operator is 0, outside the box, out here and out here, equals infinity, right? Okay. The question now is, that makes the Hamiltonian operator look a lot simpler, you'll see. What does the wave function of a particle in a one-dimensional box like this look like? Okay, well, we sort of got two cases, right? We got to think about the particle in here, right? And we got to think about the particle potentially also out here, right? All right, so what would that look like? Let's think about outside the box first, right? And that, our case here would be, what is the operator, what does the Hamiltonian operator look like, and its application to the wave function look like if x is less than or equal to 0, or x is greater than or equal to a, right? So that defines being outside the box, right? Okay, well, we could say, well, our operator, Hamiltonian, would look something like this. It would be h, or I should say, if we apply this to again, we're going to apply this to the time invariant Schrodinger equation. We'd be applying it, so it'd look something like this. Now, our wave function is only a function of x, right? Not three-dimensional space. So that's a little bit easier. And we're going to assume that this wave function is a Hamiltonian, is a excuse me, is a eigenfunction of this Hamiltonian. So that this equation, this wave function of this one particle in a one-dimensional box is valid, I guess you could say, for this situation, that the time invariant Schrodinger equation applies, right? Okay. All right, so what does that look like? All right, so think back to our discussion from the last lecture about what the Hamiltonian operator would look like for a particle moving in space, right? Remember we had that the kinetic energy was basically all wrapped up in the momentum of that particle, right? Okay. Well, but we had that Laplace operator, right, that we had to deal with because it's moving three-dimensional space, second derivative with respect to space, all that kind of stuff. Well, because we're in a one-dimensional box, that gets easier, right? So now we could say, well, we can dispense with two of the three terms, the Laplace operator, because we only have one spatial dimension to deal with. And so we can write it down pretty easily. And it looks like this. We can say, all right, well, that would have to just be minus h bar squared divided by 2m, right, times the second derivative with respect to x, right? Okay. That's the full expression of the kinetic energy operator for this particle and moving in a one-dimensional box, right, in terms of the kinetic energy. Plus, remember, for our first case here, we are outside the box, which means, again, remembering that the Hamiltonian's a sum of the kinetic and potential energy operators, that we got to add the potential energy term, and we're outside the box. And because the potential energy is infinite outside the box, we have this infinity term, right? But that's our operator. That's our Hamiltonian. So we go to apply that to this time invariant wave function, right? And assuming the time invariant, time independent Schrodinger equation applies, it should return the energy times the wave function. Okay. So now the question is, what's the solution? Turns out it's pretty easy because of that infinity term right there, there's only one solution, all right? The only way to solve this equation, to solve it for this wave function, is if the following is true. Because of that infinity term, the wave function is a function of x for dimensions outside the box here, x less than 0, x greater than a, is just equal to 0. The wave function equals 0. So if the wave function equals 0 outside the box, that means the particle can't exist outside the box. That's what a wave function of 0 would mean. It doesn't exist. It's not there. It cannot ever be there, right? If the wave function is 0. All right, that's kind of easy. All right, so what about the case that would kind of matter? How about inside the box? All right, well, inside the box, we got a situation where x is greater than 0, but x is less than a, right? Okay, so that's going to be inside the box. All right, but now because inside the box, we constrained our system so the potential energy operator is equal to 0. Again, we can write down that time, that time independent Schrodinger equation, right? We can again think about writing down that Hamiltonian. Again, we need the kinetic energy component of that Hamiltonian, so it's going to be minus h bar squared over 2m. Remember, m is the mass of the particle times the second derivative, partial second derivative with respect to x, right? But because the kinetic energy, the potential energy operator we defined as 0 inside the box, we don't have a second component to that Hamiltonian. It's all just the kinetic energy operator. Okay, cool. That's great. So now that's our Hamiltonian operator. We apply that now to that time independent wave function. All right, just a function of x, and it's going to have to equal e times the wave function again. All we need to do is solve that. Okay, now that turns out to be a little bit harder, and I'm going to skip the details of it because this involves basically solving this second order partial differential equation. It's not that hard, but I don't want to like get into the weeds. It's going to sidetrack us a little bit. So I'm just going to give you the answer, right? The solution to this, all right, so you solve the PDE, right? And it turns out the answer, the solution, if you solve for the wave function, looks something like this, right? The wave function as a function of x, turns out to solve this guy, you end up with a parametric equation. Turns out the math dictates that. And the parameter is usually given the symbol n, all right? And it equals, this is the wave function, equals 2 divided by the length of the box, so 2 divided by a, square root of that, all right, times the sine of n pi, there's x, that's our position particle inside the box, divided by the total length of the box, right? Where now n and n can only have integer values, 1, 2, so on and so on, right? So n is only allowed to be an integer, right? In the way the math works out when you solve that equation. Okay, now here's the really interesting thing. If you take this solution for the wave function, right, you can substitute this back into the Schrodinger equation, right? Here. You can substitute that solution into the Schrodinger equation, right? And the reason you would potentially do that, right? Or in this case, I should say, you substitute it, you could substitute back and it wouldn't make much difference because we're time invariant, so that's kind of stupid. What I should have said is you can substitute this solution here back into the time independent Schrodinger equation and solve for E, solve for the energy, right? And when you do that, what you find is that the energy you get out is also now a function of n, right? But it's fairly simple, right? It's n squared times h bar squared divided by 8 times the mass times the length of the box squared. All right, now look at that for a second. So we had a fairly simple system, right? We had a particle in a one-dimensional box, right? We demonstrated the particle can't exist outside the box because we set the potential energy operator to infinity. We zeroed out the potential energy operator inside the box. So really, we're only dealing with the kinetic energy of the particle inside a box, but it's got this sort of like discontinuous boundaries that it, you know, think about it bouncing off of, right? And then we solved the wave function for a particle constrained to move inside a box like that in one dimension. Solve for its wave function, right, by using the time independent Schrodinger equation. That's the form of it. Turns out to be a parameterized equation with these integer parameters. And when you substitute back in and solve for the energy, you end up with this expression for the energies that is discrete. So if you plug in the numbers, we know h bar, we know n, mass of the particle, say what the length of the box happens to be, well, we get a number, right? And then all those things are the same except for n. We go to n equals 1, n equals 2, n equals 3. Turns out what that means is that the energy of this particle in this one-dimensional box can only exist at certain energies. There's not a continuum of energies for this particle in this box. The quantum mechanics shows that this particle can only populate a limited set of energies at discrete levels speed those out a little bit more. All right, so this would be like n equals 1, n equals 2, n equals 3, n equals 4, right? Whatever. And these things are going to progress from sort of 0 energy to 1, and then, up uh, some scale. And notice that they're not progressing linearly because energy level now, this goes with the square of that number n. In this context, in a wave function like that, this number n usually gets a name, right? It's known as a quantum number. And if you remember sort of the whole idea behind aspects of quantum mechanics, right? The energy available to this particle in the system isn't, like I said, continuous, it's discrete, it's quantized, right? And the fact of that limited discrete energy levels drops out of the fairly straightforward application of the ideas of quantum mechanics to this particle in this box. And it requires that the particle can only populate those energies. Now, an analogy sometimes people use is to imagine, because this is dictated by the wave function of the particle, imagine a string vibrating between two nodes, right? That string can't vibrate an infinite number of ways spatially. It vibrates with certain harmonics. It's a certain harmonic as it vibrates, right? And those are discrete, right? As you go from sort of one fundamental to the first harmonic to the second harmonic, it's kind of the same idea that the wave function is only allowed to populate energies, or the wave function only allows the system of this particle in this box to populate energies at discrete levels. Okay, now we're going to take that idea and we're going to expand it out to think about absorption of light in a molecular system.